So let's see how much you have to spend for every iteration. So for every iteration, you have to read, you know, okay, if you can keep both two vectors in main memory, then you just have to read the matrix in every iteration, okay? In that case, in every iteration, you spend this cost. If instead you just want to keep one vector in main memory, that will be R new that you have to compute at every iteration. So whenever you have computed the new value, you store it back on disk and start the new operation, the new iteration. So in that case, you will need to read the old value, to read the matrix overall, scanning it, and then to write back the new value computed on secondary storage. It means your I/O cost in every iteration is proportional to twice, the size of the pageRank vector plus the number of entries of the matrix. So this is a short way to write the number of non-zero entry of the matrix. That's important. Not the entire matrix, only the number of non-zero entries, just because you are storing the adjacency list. And that's it. What happens if we cannot even fit the entire vector R new? So that was the case, right? So 40 billion entries, 4 bytes per entry or 8 bytes per entry, probably 8 bytes. That doesn't fit in main memory. So in that case, you can slice it, compute different slices. You divide it into k slices so that every slice fits in main memory. Then you scan the matrix, and for every slice, you update the slice. And then you do the same for every slice. There is not much you can do in that case. Okay? And for every slice, you have to read the matrix k times. Why? Because information let's say 3 slices, okay? For every slice, the update of entries in this slice may depend on each of the slices here. So to update every slice here, you need to read every slice here, and together with the matrix decide whether each entry here should be updated. Okay? You can do this incrementally, we have seen. But it means that to update every slice, so k slices, you need to, it's expensive, but it can be done. Okay? And that's the block-based update algorithm. So block stripe, that will be enough for me. Let's see some problems with pageRank, because there are problems. So first of all, pageRank measures the generic popularity of a page. it is not as so naive as in degree, for example. It's more subtle. You can have a high degree in degree, but you may not be a top ranking page according to pageRank. Just because maybe the popularity of a page also depends on how central it is in the graph. You can have a page with a high degree, but very peripheric. You only maybe reach it from certain size. In that case, the page, there is a correlation, a positive correlation between in degree and pageRank, but it's a correlation. One does not imply the other necessarily. Also, what you may not like about this pageRank is that it is one single measure of importance, so it measures importance of pages. But without telling you why a page would be important. For example, For example, consider a web page of some car fun. Maybe this page is pointing to pages that are authoritative for a certain topic, for example, for cars, giving lots of advice and so on. But maybe the importance of this page is not so high, just because it's one random user in the web. Okay? Maybe over time, if you write a blog and so on, then this page might become very important. But in principle, that does not have to be the way. And still, this page might point to relevant information, to authoritative information about cars, for example. In this case, one page like this is unlikely to be scored to be ranked very high if you just apply a pageRank randomly. Okay. At the same time, why is this the case? Because in a way, pageRank is measuring the flow, the incoming flow to the page, right? Not the outgoing flow. I mean, for example, if there were one way to say that one page points to important sources, you could also score pages according to to the extent to which they point to important pages. You see what I mean? But this would require a different notion, what is normally called the notion of hubness. So a page, for example, is a hub if it points to relevant information or authoritative information with respect to some topic. That's not the case with pageRank, not necessarily at least. We will see that there is another algorithm that was designed with this purpose in mind, and is called hits. We are not going to see it today, but be aware that this is possible. Another issue is that, in principle, pageRank can be, in a way, hijacked. What does it mean? You know spamming, web spamming? Yeah, of course. You want your website with casino, porn, and so on to score high. Normally, if pageRank were always doing its job, these pages shouldn't rank very high, because they don't really they are not very authoritative, how should I say, unless you do you have some query about porn. In that case, maybe they are relevant. Okay, but still, the owners of these websites very normally try to, let's say, enrich their pages with information that should increase their score, their ranking score, both manipulating the text and the link structure. For example, they add a lot of fake pages pointing to these pages, right? That is called altogether spam. And when you use links to manipulate the ranking score, it's called link spamming. Of course, the very moment you try, actually the idea, one of the reasons why pageRank was invented in the first place was to mitigate link spamming. Because at the very beginning, people were simply building what are called link farms. So, for example, 10,000 pages pointing to the same page. If you apply in degree as your ranking score, of course, if you instead use pageRank, this problem is going mitigated because a high ranking page will get its rank from the entire web and not just pages that are close to you. Okay? So let's say that pageRank addresses some forms of link spamming, but it does not address them all. There is always a war between spammers and search engines, because of course search engines have the objective of providing authoritative information sources, whereas very often the goal of spammers is the opposite. Okay, we will maybe come back to that. Yeah, let's say solution. This is one solution. There is a number of solutions. And no solution is the silver bullet, okay? Whenever you find a new solution, spammers will come up with a countermeasure and vice versa. So there is, disarm conflict. Now, let's come to something else. Where is it? Yeah. I want to show you something. So I gave this, this query to Google, profiling, and I get a page of results. Now, let's say that I'm interested in the second. I'm interested in this entry. Yeah? So what happens? I click on this. And I jump to the page about profiling. So, nothing strange. But I invite you to look at what happens when I place my cursor on the link. You see, the link is not pointing to the page. Okay, actually it's pointing to a script. This is the link. But this is a script. Why? Because in this case, the search engine is tracking my browsing habits. I mean, to the extent to which it can. Okay? So it's acquiring information. So which sources of information has the search engine in this case? In this case, at least two. One is the query I submitted, so profiling. The second is the page on which I'm going to click. In this way, the search engine, for example, knows that the word profiling in my single-term query, which is hard to tackle, actually was referring to the TV series, to a TV series. This is very precious information that can be leveraged. Why? Because these people have to make money somehow. How do you make money? One of the most important sources of money in the web is personalized advertisement, right? Let me see if I have another interesting example. I don't know. No, maybe not here. Maybe here. Let me see. They are not. Today I'm not being proposed anything. But there is a lot of advertisement here. This is, for example, advertisement, and it's not clear that actually. It's not clear that you would see the same advertisement. Oh, I clicked on this. Now I'm going to be bombed. I'm going to be bombed. You see? That one trick to clean up your liver. Now, they have profiled me. Actually, I provided false information. I'm not very interested in the topic, but still, I provided one piece of information. So what does it mean? That your browsing behavior is actually a precious form of information. It reveals something about your interests. A search engine or another website is not really interested in who you are. Actually, that's pretty irrelevant. But it is interested in which pages different users link or visit. Okay? Why? Because these pieces of advertisements normally are placed on these pages on the hosting website through a bidding. So these people bid money to see their advertisement placed whenever certain users visit the page. And the users are provided with this information, with these advertisements, depending on their browsing behavior. So this information has to be collected and transmitted and processed in some way. Why am I saying that? Because profiling is at the base of what is called competitive advertisement, online advertising, and other stuff. It's also used to, for example, provide you with information that is closer to your interests, you know? There is a book about this, The Filter Bubble, it's called, that actually discusses what happens when search engines start doing profiling of users, and so they are likely to provide you with contents that you are more likely to be interested in. On one hand, this looks like a better service. On the other hand, this, in a way, limits, let's say, the material and the points of views you are exposed to. So there is a trade-off. There is a balance. So if these are the implications, let's start to look how this is done. And we can start doing this with one specific example, which is the example of pageRank. So we have seen that pageRank actually is, in principle, the original algorithm does not do any form of profiling. I mean, it's just a random walk, and it will provide every page with a score that reflects its centrality in the web, right? That's all. But at some point in the early 2000s, so people started to think that perhaps whenever different users might be interested in different topics. Some people might be more interested in sports, others in celebrities, others in politics, and whatever. So one question is the following. Is it possible to apply the pageRank idea, but biasing the pageRank for different topics? For example, could I try to identify in the web a ranking of pages with respect to sports or to celebrities or whatever? Can I do that? The first question is how. The second question is this feasible? Remember that you can come up with a solution, but perhaps the solution is not feasible. For example, if the solution requires you to recompute every time a new pageRank vector, a global pageRank vector, I mean, it's, there is some scalability issues. You go to Brilliant Page and say, look, this is my algorithm. They will say, nice, this is not going to scale. Sorry, you can drop your idea. Okay? So, that is the goal we have. Can we do that, and how? Why did I show you that first example? Because we can assume the following. That if you consider one specific user, you could, over time, collect information about the pages that the user was visiting more frequently. I mean, of course, this information will never be global. You will not have full information, but you may have enough information to be statistically significant. For example, if these are the end pages of the web, you might know that for a given user, for example, all pages covering, I don't know, these pages were never visited by that user, for example, according to the information you have. You might discover that most of the pages visited by this user were concerning sports, moderately, I don't know, politics, books, and so on. Okay? So, in principle, if you were able to collect this information for every user, you could come up with profiling vectors, essentially vectors that summarize the interests of the user according to her browsing history. Okay? You can also look at this as a probability vector, a distribution, the frequency with which you visit every page. And the frequency has to sum to 1. Okay? That's interesting. It looks like a distribution. Can we use this? Sorry, you can also do other stuff. For example, you could be interested in pages that are relevant for sports. Pages that are relevant for sports. It means that, for example, of all the information I've collected about users, I will just take pages that are, no, sorry, I could do another strategy, not with respect to a specific user. I could myself represent the profile, the ideal profile of a user who is only interested in sports. How would that profile look like? Well, maybe it could have just I don't know, some 1 over S here, where S is the number of pages related to sports, and 0 otherwise. Okay? That's another profile vector. Or it could be different, because, for example, I compute the pageRank of all pages, then I just look at the pageRanks of the pages about sports. I renormalize everything so that the result is 1, and then I have a rescale pageRank vector only for the sports pages. You see what I mean? I can do many things. Which one is the best? You try, you test, you see how it behaves, okay? So, why am I saying that? Let's go back to our friend. Let us assume that I wanted to rank the pages based on the topic sport. So I want to find the pages that are more relevant, that are most authoritative for the topic sport. Notice, they do not necessarily have to be pages related to sports, okay? They can be any pages, but in some way they are relevant, their ranking score should reflect the fact that they are somehow related to sports. How can I do that? One way to do this, let me see if I have a slide. Yes, I have a slide. Is the following. When you apply teleportation, you do the following trick. Instead, in the standard pageRank, whenever I do a random jump, I'm jumping to any page uniformly at random. What happens if I modify teleporting and I simply random jump to any page related to sports uniformly at random? The pageRank changes in that way. Do you agree with this? Yes. In particular, if this page is related to sports, I will also have this term. In this case, this should be 1 divided the pages that relate to sports, the number of pages that relate to sports. If J does not refer to sport, the only way to reach J is through some link. Now, which are the consequences of this fact? Well, there is a number of consequences, actually. For example, what might happen is that it is no longer true that the entire Markov chain you get is aperiodic and so on. But still, you will have a sub-Markov chain at least that satisfies. You have an irreducible class that satisfies. Actually, you don't even have periodic states, actually. Why? You don't have periodic states because at every point in time you can scramble things because you can jump uniformly at random to some subset of pages. This is enough to remove periodicity, okay? Even if you were jumping to one single page with some probability, that would be enough to remove periodicity. So actually, periodicity you remove. And actually, if you have already removed dead ends, essentially, no, the Markov chain could be reducible anyway, because you're not jumping uniformly at random to every page, but to a subset of the pages. What happens if the Markov chain has become reducible? Nothing bad in this case, because the Markov chain anyway will not be periodic, so you will have a stationary distribution. The only point is that since you're always starting from a subset of pages that belong to this set, if you have another class, if you have another subset of pages that is not reachable from here, all those pages will get a 0 degree, a 0 rank score. But that's not bad, because that's actually what you want, because probably those pages are not related to sports. So they get 0, fine. They get a small rank score, okay. It means that somehow they are related, okay? And the algorithm is still working. Why? Because we can always do the same trick. And how? You remember the way in which was it A, the matrix? A? I was using A for the matrix, the transition matrix. A, right? Oops. This was the old matrix. So what is changing here? Only one thing is changing. Instead of having this, I will only have, here I will put, and instead of having this, I will have some P of t with okay? Actually, what is I've written here is the same as is written there. Yeah? You should convince yourselves. It is the same. I just have 1 minus beta divided cardinality of S here. So if you put this inside, then it becomes that. Okay? But you realize that this is the very same algorithm I've written. Notice also the following. That the vector P divided by cardinality of S is still a probability vector. So it's a distribution. Only it is a distribution that has puts mass 0 to certain pages. Also, when I take the product between this and this, again, I get a 1. So this is equivalent to the pageRank vector with the only, the random walk, the pageRank random walk with the only following difference. Whenever I am at some page, with probability beta I follow the links, with probability 1 minus beta, I jump uniformly at random to any of S possible pages, where the S possible pages now describe some topic of interest. Okay? So, there is a number of questions to ask here, because this seems to work. I again obtain a stochastic matrix. The matrix is, again, either ergodic or there is a subset, a subgraph that corresponds to an ergodic chain, which is enough for me. It means that some states, some pages will get a 0 ranking, but I don't care because they should get a 0 actually. As for convergence, speed of convergence, actually it depends on this parameter again, so I can use this as a knob to decide how fast my power method should converge. The algorithm is the one I just showed you. Not much changes. Which are the questions we have to ask? Well, there is one question, one important, actually two important questions. First of all, how do I compute these vectors, which are called personalization vectors? I mean, it seems something obvious. So one way of collecting them is using information you collect about the users, which can be done to some extent, but that is very fine-grained information. So it's very, for every user, you have very specific information. Sometimes that's not necessary. Sometimes we just want to have a coarser-grained profiling, for example, sports, or music, books, movies, okay? For example, how do I find a personalization vector for movies? Do I have to profile users to the purpose? Actually, no, you do not normally have to, because there are some very nice repositories of high-quality web pages for different topics. For example, there used to be DMOS. Yeah? Millions of pages categorized, high-quality, humanly classified pages for different topics. So once you access the web pages, you can build your profile vector. You pick everything on DMOS that is related to movies, and you have a personalized vector, a personalization vector for movies, and so on. You can proceed in that way. But now, the second issue. Assume that in the end we are interested in the users, right? I mean, we want to have topic-specific, this is called topic-specific pageRank. So we want to have a pageRank tailored for different topics, but then we want to use it. Why? Because we would like to provide personalized information to different users. To this purpose, we can have information about users' habits. For example, how frequently a user clicks on a page concerning music, how frequently she clicks on a page concerning movies, and so on. So let's say that I know that 30% of the time a user will click on whenever she enters a query, 30% of the time she will click on some movie-related page, 40% of the time on some music-related page, and 20% of the time on some books-related page. Okay? In that case, I would like to modify this personalized pageRank, this personalization vector. I would like to have a vector in which you have entries related to music, movies, and let's say, what was it? Books. Yep. What was it? Okay, let's say that I've collected this information about some user, Alice. Now, I would like to leverage this information. Notice that this is not a personalization vector. This is just a vector that has as many entries as the number of possible topics that I've decided. I may decide, as Google, I can decide that the main topics I want to consider are 100. So in that case, this vector would have 100 entries that have to sum to 1 for every user, depending on how frequently she follows the links of pages related to a given topic. Now, assume that for this user, I collected this information. So 30% of her time on books, 20% of her time on movies, 50% of her time on music. Now, proceeding as I said before, what I can compute is I can have personalization vectors that describe the topic music, the topic movies, and the topic books, right? Okay. In this case, if I have 100 possible topics, I could compute 100 personalized pageRanks for each of these topics. But now, if I want to compute a personalization topic for Alice, a personalized pageRank for Alice, that's a problem because I should use, do you see that I should use a new personalization vector, P, that is 0.3 P books plus 0.2 P movies plus 0.5 P music. This would be a personalization vector that describes Alice. Do you agree with this? Once I have computed this, I apply personalized pageRank, I run pageRank, and deliver a ranking on the entire web for Alice. You see, is it clear? I mean, I don't want to say whether it makes sense. I want to understand whether it is clear what I have in mind and whether it is in principle possible to do this. Just, okay, let us recap. I have a number of topics that the search engine, decide. They can be music, movies, and that is my business. I can have 10 different topics, I can have 100. Every topic is described by a different personalization vector so that I can apply that algorithm. If I have 100 topics, I can pre-compute 100 pageRanks, one for every different topics. These pageRank vectors will be different in general because they will give different scores to the same page depending on the topic. You agree with this? Fine. So if I have a user that is explicitly interested in music, let's say she's only visiting music pages, it's easy. I just pick the personalized pageRank that I've computed for music, and I'm using that for that user, right? But users are humans, so some people are maniac, but most of us are not, fortunately. So a single user will be described by some linear combination of these different different tastes, right? Even in the simple case, let's say only 3 tastes, it will be correspond to a linear combination of some personalization vectors. How many possible linear combinations I have? As many as the users. So if I wanted to build a personalized pageRank for a given user from profile information I have about this user, I should every time to recompute pageRank from scratch. You see the point? Is that realistic? What are Breen and Page going to say when you come up with this proposal? Huh? Think about and then come back. You either tell me how I can compute this without recomputing everything from scratch, if it is possible, or this idea is not feasible. Okay? Well, what is these slides? They are not telling me. Okay, there is something I have to tell you. Actually, I have notes about that too, so I will just post them on the website. And they are on the book, okay? On the book by Raghavan and so on, you find what I'm about to tell you, so you do not need to take notes. But let's assume that the following. Let us assume the following, that I have personalization vectors, let's say P1 and P2. So I am computing the pageRank for these 2 personalization vectors. What does it mean? I'm computing 2 stationary distributions, approximately, that will satisfy the following. Is this enough? What do I need? Do you agree? The personalized pageRanks for these 2 personalization vectors could be this. I say could be this because in general, it is not sure that I want to weigh all the pages that belong to the set S in the same way. You see what I mean? Is it clear what I say? So this corresponds to the case in which, for example, P has a 1 for every page in the set S1 and 0 otherwise. But actually, I could have different ways. In general, I will have 1 minus beta, 1. The more general form is the following one. With a caveat that's all. That's all I need. So in general, P1 and P2 can be any probability distributions. Okay? That is a special case. Is it clear? Yes or no? So I have redefined P1 and P2. Before, P1 was a vector containing 1 or 0, but then you had to divide by the number of topic-related pages. Here, P1 is just a probability distribution, not necessarily uniform. Okay? This is the most general case. And this is still topic-sensitive pageRank. So let's say that I have these two vectors. They correspond to two topics, and I already have computed this. So you know, you don't want to recompute pageRank from scratch whenever a user submits a query. Come on, that's not serious. So these vectors, these personalized pageRank vectors, you already have stored somewhere for a certain number of topics, perhaps 100 topics, not more. So they are already there. Now the question is the following. Assume that a user submits a query, that a user actually can be expressed as a linear combination of P1 and P2. So let's say that the profile for the user, according to what she did in the past, can be summarized as a linear combination of P1 and P2. Is there a way to compute the pageRank that corresponds to this profile without recomputing everything from scratch? Yes or no? Is it clear, my question? Blank. Blank. Just to be clear, I want to compute the following. I want to compute a vector that corresponds to this personalization vector, where this personalization vector is this, a linear combination, where alpha 1 plus alpha 2 is equal to 1, because in this way, this is still a probability distribution, right? Of course, you can generalize this to any linear combination of your personalization vector, okay? Now, is there a way to quickly compute this without applying the power method to this equation? I mean, that's horrible, you know, for every user, that's unfeasible. So can we make Brilliant Page happy? Well, let's see. One first thing to remember, not to remember, actually to notice. One first thing to notice is the following. When I apply the power method to either this or this, I obtain a stationary distribution and one single unique distribution. Why are these two distributions different? I mean, some of you might be confused. But didn't you tell us that The random walk corresponds to an ergodic chain, so the distribution is the same regardless of the initial state. Yes, but here we are changing the matrix, right? So these two matrices are two different Markov chains. Let's call them P1 and P2. Okay? They are two ergodic Markov chains, but they are two different ones. Now, let us see what this is telling us. Why can I say this? Because the Markov chains are ergodic, and so there is a stationary distribution, so this exists. What happens if I take a linear combination of the left-hand side according to these two coefficients, alpha 1 and alpha 2? So, what is this equal to? Wait, because there is some subtlety here. Right. Okay. I mean, yeah, so what? I should prove that this is equivalent to this. Then I would be okay, right? Let's see if this is true. Written like this, I'm not discovering anything interesting. I'm just taking a linear combination of stationary distribution of two Markov chains. But the question is the linear combination equivalent to the stationary distribution? For example, is this the same as RT? If this is the same as RT, I'm done, right? I just take the two pageRank, I take the linear combination, and I'm done. This you can do. That, applying the power method, no. Okay? Is it that I'm so lucky that this is true? Yes or no? Let's see. Let's try to expand this. If you expand this, you will realize that each of these has one component, these two matrices have one component that is always the same, beta alpha, right? So actually, what I'm writing here is, you correct me if I'm wrong, okay? Am I correct? Now, when I multiply this by this, I have to remember that this is a probability distribution. Multiplied by this, I get a 1, right? So, do you agree? Good. Then maybe we are coming close. Huh. Look at the beauty. Yeah? I mean, P. This was our personalization vector, right? R. This is equal to this multiplied BA. Haha. Okay. So I think that was J. Widom in 2002. This is called topic-sensitive pageRank. Now Brin and Page can say, okay, you can do it. How does it work? I do the hard work of computing pageRank, topic-sensitive pageRanks for 100 topics. At the same time, I collect profile information for users so that I know how important each topic is for any given user. And how do I do this? A vector of probabilities. Let's say with 100 entries. Whenever I want to compute the personalized pageRank for a given user, I just look at how every topic is important for this user. I weigh every personalized pageRank with the corresponding degree of importance, and I take the linear combination of the pageRanks. End of the story. Of course, typically, I'm not going to do this for every single user. I will classify users in, I don't know, 1,000 categories or so. So I have users that have a more sports-oriented profile. You know, you don't do this for billions of users. You do this for 100 classes of users, perhaps. Okay? But what is important is that you can compute this on the fly if you wanted. It is something that is still doable. In principle. Of course, as the web scales, it becomes more even computing a linear combination of two vectors takes linear time. When the number of components is billions, it becomes hard. But then you can play with this. Let's say this is in the realm of possibility. This is not in the realm of possibility. With this, you can play a bit, tweak it, and you get something. Okay? And we are just lucky. Linearity. That's all we needed. Okay? So, notice one important point. It's always important, and this is a very, how should I say, this is a characteristic case. Analysis is not used to show you what you're doing. It is only to show you that if you do this, it is like doing this. Analysis is not necessary to run the algorithm. Analysis is only useful to understand why it will work. That's all. Okay? And here you can go over yourself. 16 categories. We can do this. 16 personalization vectors. That's nothing. Now, I have only 5 minutes. What comes next? Let's say that, okay, I don't know if I am assigning this for the exam and so on, but I'm just discussing this briefly in the 5 minutes we are left to show you that these notions are not only related to pageRank. Very often you apply algorithms like pageRank or related stuff to do quite different things. I mean, pageRank does not exist for the web only. Actually, nowadays, pageRank is just is just one of the 100 or more indices that decide how important a page is for Google or another search engine. It's not even the most important, probably. But the idea behind can be very useful in other areas. So, for example, assume that you have a conference, a list of conferences. Sure. So assume that you have a standard, let's say a standard example. you have topics, you have conferences, and then you have names, orders. So let's say for every, you have an order, and then you have a link to the conferences these people submitted to, right? And then you want to, for example, these are existing people. These people exist really, each of them. So, and these are mostly artificial intelligence or mining, information retrieval related conferences, data mining mostly. And you would like to understand, for example, you would like to classify, you have a conference and you want to know which are the most similar conference to this one based on submission, based on the people who submitted to these conferences. How can you do that? One way to do that is, for example, to say that two conferences, first of all, to obtain from this graph, from this bipartite graph, a graph in which, for example, you say that there is a link between two conferences whenever at least one order submitted to both conferences, and then perhaps you add a weight on the link depending on how many orders happen to submit to both conferences. You see what I mean? Is it clear? So from this is a bipartite graph, right? I can obtain from this graph a graph on the conferences only by adding links between conferences whenever one order, at least one order, submitted to both conferences. For example, we have Philip Yu submitted to both KDD and AAAI, and so I have a link between KDD and AAAI. Then I can add weights to the links depending on how frequently someone who submitted to KDD also submitted to AAAI. Not the same paper, different papers. So eventually I have a weighted graph. In this case, actually an undirected weighted graph. But even if it's undirected, I can run pageRank or a variant of pageRank. So this one variant of pageRank is called simRank and is used to measure similarity between vertices of a graph. In particular, what you do is the following. You run personalized pageRank with a personalization vector which has a 1 corresponding to ICDM and 0 otherwise. You compute another pageRank vector with personalization vector 1 on AAAI and 0 otherwise, and you compare the corresponding pageRanks. If they are close, then you say that the two conferences are close. Makes sense, right? Because it means that if you start a random walk from those two vertices, you tend to visit more or less the same pages with the same frequency. It's a measure of similarity. If you do this on this example, you get something like this, which is actually, I have an idea of these conferences, and I can tell you that this makes sense. For example, KDD will be mostly similar to ICDM, which is true. ICDM is the International Conference on Data Mining, and KDD is probably a top conference on data mining, knowledge discovery from data, it's called. Okay, Sigmod is related, but it's more database oriented, even though you can have something on data mining, and so on. Okay, PKDD and PAKDD are more or less satellites of KDD, so. Just to give you an example. Okay, so pageRank and stuff like that is actually much more powerful than you think. It can even be used, for example, to find partitions in graphs. So, for example, if you want to find, let's say that you have a graph in which vertices represent people, and you have links depending on, I don't know, anything. Participation in the same social network, I don't know, Facebook friendships or whatever. If I give you one vertex or a small set of vertices, can you find the subset of vertices that in some sense are closest, define the community to which one person belongs? Can I do that? There is a number of ways to do that, but most of these, the most effective ways to do this are variants essentially of personalized pageRank. Okay? And there is also some theoretical analysis that explains why this may be a good method to uncover such communities. Okay? So be aware that actually pageRank is not something you do for the web, Google, and so on. No, there is much more to it. than it seems. And I'll see you either Thursday or Monday. I don't know yet. I have to decide. And that will be all for today. Thanks.